Hello again. This is the chapter on the video on chapter 13, and this is the last chapter of the textbook, and of course the last chapter that we cover in this course. So let us get started. I'm going to start by, of course, running that PowerPoint file that we have in chapter 13. So let us get started. So far, we have talked about many different distributions that we have used in previous chapters. For example, we have seen, I'm talking about all the continuous distributions. We talked about uniform distribution, right? So x was between two numbers. And then we talked about exponential distribution, something like that. And then we talked about normal distribution, the standard normal and just the regular normal distribution. Then we talked about if it's a standard normal, we call it z, right? And then we talked about t distribution, which is very similar to normal distribution, the same shape. The number in the middle is 0, just like normal, right? And a normal distribution has mu and has a standard deviation. In fact, all of these do, right? The t distribution had something we called degrees of freedom, right? And that was the sample size minus 1 for the applications that we were talking about in other chapters, chapter 9, chapter 8. Now, if you take a bunch of z values, right, like, z1, z2, and so forth, all the way to z, maybe k, and then square them and add them, then we know, we talked about that in chapter 11, this number will give us a number we call chi-square, right? And the chi-square distribution looked like this. And we used it in chapter 11, right, for many applications, including the goodness of fit test, right? So that is a chi-square distribution. So we got all of these, that's so far 5 different distributions, right? In this chapter, we need another one to do our work, and that is similar to this, what we did here, which is taking z values and squaring them and adding them. Now we're going to take a bunch of t values, like t1, t2, t3, and so forth, to k, square them and add them. And this is going to result in a number called f. So we're going to talk about f distribution. And f distribution looks kind of similar to chi-square distribution. And this is what we are going to use in this chapter, f, to do the work we want to do in this chapter. Okay, so let's get started. So in this chapter, we're going to talk about the f distribution. So we're going to interpret what f probabilities are using the distribution. And we're going to discuss 2 applications of f distribution. One is called ANOVA, which stands for Analysis of Variance. And that's what we're going to do in this chapter. And then another thing we want to do is we want to do a test called tests of 2 variances. All right. So let's we're going to discuss this at the end of this chapter. And then mainly right now we want to talk about all of that. All right. So for hypothesis test comparing averages between 2 or more groups, Now, in chapter 10 that you were to read by yourself, remember we didn't include it in the tests, but in chapter 10 we do something like that. If we have two mu's and we don't know about them, now the question is, we can compare them, and we did that in chapter 10. So in chapter 13, now if we have two or more mu's, right, and we want to compare them, we can use this test, which is called ANOVA, analysis of variance test, ANOVA. Okay? All right, now how it works, in a second we're going to talk about that. So the purpose of one-way ANOVA, which is what we want to do here. So one-way ANOVA, that means we have only one factor, right? And we're going to compare the mu's based on just one factor. Again, we're going to discuss that. There is also a two-way ANOVA that we are not discussing in this chapter. Okay? All right. And the test actually uses variances to help us determine whether the means are equal or not. And again, I'm going to talk about that in a second. So there are 5 assumptions that we have to have satisfied before we can do this. So let's talk about those first. First of all, that each population that the samples come from have to be normal. So basically what we have assuming we have bunch of populations, and then we take samples from each population, and in each sample we're gonna estimate the x bar in each sample, and then of course these x bars are estimates for mu1, for mu2, and mu3 that we don't know, right? So these are estimates that we don't know. So I mean, there are the parameters that we don't know. So we take samples and we estimate them using the sample statistic. So the question here in this test we want to do is that whether mu1 is the same as mu2 is the same as mu3. That means whether they come from the same population or they come from 3 different populations. That's the question. Of course, the test doesn't answer that. The test only answers whether one of them is different from the others. So if this is the null hypothesis, the alternative hypothesis would be that at least one of these is not equal to another one. Maybe this, or maybe mu1 is not equal to mu3, or mu2 is not equal to mu3, things like that. So what we are going to do in this test, we're going to use the F distribution. And again, I'm going to talk about that in a second. But we use F distribution and we use p-value to decide whether we're going to reject this or not. So if we reject it, that means we have enough evidence to say that they don't all come from the same population. If we don't have evidence, then we fail to reject, right? Then we kind of say that we don't have evidence against this idea that the mu's are the same. Okay, the samples, of course, are randomly selected and independent. The populations are assumed to have equal standard deviation or variance. That means even though we think they're coming from different populations, if possible, we assume that those populations have the same standard deviation or variance. The factor is categorical and the response is numerical. Again, I'm going to give you some examples. So right now maybe it's a little vague. So let's talk about some examples. So here we have 3 different traffic routes that are tested. So people have gone through these 3 different routes, and then these are samples of. So people in general, the drivers, can take any route, right, at any time. So we don't know the populations, but we know we took a sample. We took a sample of these 4 people driving on this route, and then found out how long does it take them to reach the destination using the route 1, and then using route 2, and using route 3, right? So here the categorical variable is this variable up here, right? So the factor is a categorical variable, and that is the traffic route. And the values of that variable are route 1, right, route 2, and route 3. Now the response variable, the response is the numerical variable driving time. How long does it take each person to go through that route to reach the destination? That long. So the question we're answering in this chapter is, for example, if we find the x bar 1 here, and x bar 2 here, and x bar 3 here, and the null hypothesis is that mu1 is the same as mu2 equals to mu3. So if we don't find any evidence against this null hypothesis, it would mean that it doesn't really matter which route people take, right? The mu's are the same. So of course we are not going to get the same x bars here. We will get different x bars, but the question is, are these x bars different enough for us to reject that or no? That's the idea that's the question we want to answer here. Okay? All right, let's look at another example. Here we have, suppose that the following data are randomly collected from 5 teenagers in each region of the country. So we have north, east, south, west, and central and east. And from each region, we took how many teenagers? Looks like it's 4. It's 5 teenagers in each region of the country. The numbers represents the age at which teenagers obtain. So it should be 4 here. I made it 4. So in each region of the country, the numbers represent the age at which teenagers obtain their driver's license, right? So the factor is the categorical variable region with 5 values, and the response is a numerical variable age at which driver's license was obtained, right? So here, so basically we took sample of 4 teenagers from each region, and then recorded the age at which they got the first driver's license, right? That's it. Now again, we get we get x bar 1, x bar 2, and so forth, right? X bar 3, x bar 4, and x bar 5. And now the question is, again, the null hypothesis would be whether these mu's are the same or they're or they are different. So if these mu's are the same, if we don't have any evidence against them, that would mean it doesn't matter where you live in these regions, right? Your driver's license, the age that you get your driver's license is not really that different, right? All right. So we test the null hypothesis of equal means of response in every group versus the alternative hypothesis of one or more group means being different from others. So the null hypothesis says that they're all the same, and this k is number of groups that we have, right? Number of values that the categorical variable has, right? And the alternative says at least 2 of the group means are different. All right, so let me give you an example and how we do it in this course. We use a calculator. So here are three sets of numbers. Think of them as three samples. Now the sample sizes don't have to be the same, okay? The sample sizes don't have to be the same. So these are three different sample sizes. We have, this is 4, 3, and 5. So N1, N2, N3 are sample sizes of different samples. And then X1 bar, X1, X2 bar, X3 bar are the averages coming from these samples. All right. Now, the question we want to answer is, are all these mu's of the populations that they come from the same or are different? So now here I created this on purpose for them to be from the same population. And what's the population they come from? What I did, I just created, randomly I sampled bunch of numbers from 1 to 6, integers from 1 to 6. First I picked 4 integers randomly, and I created L1 here, which is that. Then I sampled 3 numbers from 1 to 6 with this feature, which is under math probability on your calculator. And I can quickly show you. So the way I did was by going to math, probability, and then I pick random integer, and then 1, 6, let's say 4. And I pick 4 numbers. Obviously I'm going to get different numbers, right? Because they're random. So this is what I did. And so obviously these come from the same population. They come from the population of integers from 1 to 6 randomly. And I picked the samples randomly. So satisfy the condition of one-way ANOVA. Now, so the test is like this. I'm going to put these numbers in L1, L2, and L3 as 3 samples, right? And then I'm going to run a test on the calculator. It's called ANOVA. See? So where is that ANOVA test? Is on there. Well, looks like I have 2 calculators. I don't need 2 calculators. Okay, so that test is under stat, test, and is the last one. See? Go ANOVA. And then what you do, let me make sure I have my L1, L2. No, I don't have anything in L1, L2. I can't do it right now. But I can put them in there and keep them for later. 1, 4, 5. So you go to stat edit, you know that by now, right? And L2 is 1, 4, 3. And L3 is 4, 4, 6. Another 4, and then 1. Okay, so we put the numbers in there, and then we do the ANOVA. We get ANOVA from a stat test, and we just put L1, comma, L2, comma, L3, and then press enter. There, the test is done for us. That's our p-value. See that p-value? So this right here is our p-value. And this is F statistic. This number right here is F statistic. So let me erase that so it won't be in our way. So this is the p-value. And this is a F stat. I'm going to explain where F stat comes from and where p-value comes from. But that's how we do it, and based on p-value, we're going to reject the null hypothesis or fail to reject, just like chapter 9, right? Now, where does that F come from? Where does it come from? I'm going to talk about that in a second, and how we get the p-value. So the distribution is going to be F distribution like that, right? And then f that we find, the number f, which is our test stat right here, we're going to put it over here, whatever f is, and find the area to the right of it. And this test is always a right-tailed test that we're going to do. So we're going to find that p-value. If the p-value is less than, if it's less than alpha, we reject. That's the idea. It's very simple. So doing the test with the calculator is very easy, but understanding where it comes from, what it means, and then getting the result, all of that requires some work, so we're going to do in this chapter. All right, now in terms of where f comes from, the idea is this. The idea is that if these three groups come from the same population, so if all three of them come from this one population, then that population has some variance, right? So we're going to look at the variances instead of looking at means. Instead of looking at x bars here, we're going to look at variances. So we say the original population has some variance. If these come from the same population, then we're going to divide the variance of the population into two types of variance. Now by variance I mean variation, right? So we're going to divide it into two types of variation. One variation is the variation with respect to what? The grand mean. You know, every group, every sample has a mean, right? x1, x2 bar, x3 bar, they all have a mean. And there is a mean of the means. That means you put all the numbers together and divide by 12, which is the sample size, right? So that's what I mean by what? By grand mean, right? So there are two types of variations. One is the variation with respect to that grand mean, right, per group, right? So is the variation, amount of variation per, with respect to what? With respect to grand mean per group. So the unit of this variation is this, unit of this rate is variation per group. And then another variation is the variation of the numbers with respect to their own group means, right? And that variation goes in the denominator. And that variation is, the unit of it is per item. So variation with respect to grand mean per group, and the variation with respect to group means per item goes in the denominator. Now, if we assume that these come from the same population, then the numerator and denominator are basically the same number. They approximate, they estimate the same number. So if they don't come from the same population, then the numerator ends up being bigger variation than denominator. So we're going to look at the formulas for these, but the denominator is basically an estimate of the original variance. Remember, if you put all of these together, right, and find the variance of these 12 numbers, that's an estimate for the sigma squared. And this also is an estimate for that. This number right here, as I said, is a variation with respect to what? The grand mean per group. Now, the ratio ends up being that number that we want, f. So f distribution has 2 degrees of freedom, is a ratio, and has 2 degrees of freedom. 1 degree of freedom, degrees of freedom, is the numerator's degrees of freedom, and the other one is denominators. So the numerator's degrees of freedom is basically, you want the variation per group, and we have 3 groups, but we calculated the grand mean, so we lose 1 degrees of freedom. So degrees of freedom for the numerator would be k minus 1. K is number of groups we have. In this case would be 3 minus 1. And so numerator's degrees of freedom would be k minus 1. And the denominator's degrees of freedom, now the denominator, remember, is variation per item. And how many items do we have here? We have 12. But we calculated 3 means in order to be able to find variation with respect to those means, right? And those 3 means reduce the number of degrees of freedom to whatever it is minus 3. So formula for it would be n minus k. This should be a little n. Later we're going to see this little n is just the sum of these n's, okay? So n minus k is the degrees of freedom of the denominator. And then this ratio gives you a number under this distribution. And this distribution, the 1 is about right here somewhere, right? So if they come from the same distribution, this ratio would be 1 or smaller. If they don't come from the same population, then this numerator would be bigger than the denominator, and this number f gets bigger than 1. Now how much bigger than 1 it gets, that determines our p-value, of course, depending on what it is. If it gets big enough than 1, then we reject. What do I mean by big enough? Big enough so that the p-value is what? Smaller than alpha. Then we reject. All right. So again, the calculations are done with the calculator easily, and the p-value is given, and we can easily make the decision based on the calculator's result, right? But let's talk about these concepts. First of all, where formulas come from. First, I want to give you the formulas, and then I talk about why the formulas are the way that they are. So there is a total variation, which is basically taking all the items in the group and subtracting what? The grand mean. So x double bar means the mean of the means here in this problem. So if you find the mean of all the numbers involved in all groups, and then use all the members of all groups, and then subtract the grand mean from them and square and add, we get the sum of squares, that's SS, sum of the squares total, which is basically that, right? So sum of the square deviations from what? From grand mean would be this. Now it turns out that sum of deviations is actually sum of 2 SS, and those SS are SSB and SSW. So SSE is the between variation. What do we mean by between? That means if you have many groups, each of them has an X bar, right? So this is the sum of the variations of all the numbers from their own group mean, right? So that's SSB, sum of variations from their own group means squared, of course. So sum of the squares of variation from the means of their own groups. That's what this is. And this one is the sum of the squares within. That means is the sum of the square variations from the grand mean given the 3 groups, right? So now this is, of course, sum of the square deviations from the grand mean, but this one assumes that there are no groups. right? If there were no groups, that would be the sum. But since we have groups, and groups can have different sizes, so this might be n1, n2, n3. So the contributions that the members make, the contributions that group make, depends on the size of the group too. So that is taken care of in this formula. All right, so, and n is of course the sum of the sizes, sample sizes. And here are the two formulas. SSP is that, and SSW is this. Now, remember in variance, when we calculate the variance regularly, in previous chapter, we had xi minus x bar squared, right? This is x bar, and then we take the sum and divide it by n minus 1. Remember how we calculated the variance? Now it's similar idea here, except that we separate the sums and then we decide what to divide by. So MSB is the mean square variations, as the mean square is basically the variance for what? For the variation with respect to the group means, right? That's what that is. So we divide that sum by k minus 1, which is number of groups minus 1 together. And this one is the variance with respect to grand mean, which we call it the, MS within, and this is MS between. So what is that? Well, remember the unit of this was per group. So the unit is variation, right, per group. So the denominator should be number of groups minus 1. And this one is variation per item. So variation per item, how many items do we have? Well, we have n total minus what? Minus 3, because we had to calculate 3 means, and we lose 3 degrees of freedom. So that is variation per item. So that's what the denominator is, that. Okay? The total degrees of freedom would be the sum of these two. So notice that k minus 1 plus n minus k, the k's go away. So that's just n minus 1. So n minus 1 is the total degrees of freedom, and that is what we do if we find the total what? If we want to find the total variation per item, regardless of groups, that's what we have to do, right? All right. So F, of course, is the ratio of this over, ratio of this over that, right? And the degrees of freedom of the numerator is k minus 1, the denominator is n minus k. So that's the idea. So let me try to explain where the formulas come from. Now, the real math behind this, if you want to know where the formulas come from, requires you to know how to expand double sigma notation. So this is going from some number to some number, and this one goes from some number to another number, right? And we got some expression here, so you got to know that. And that in this course we don't have. So we're not going to use that idea to prove what's going on here. We're going to see if we can prove it without, not prove it, but understand it without using double sigma notation. So here, why is the formula look like this? Well, it says what? It says N1 is the number of members of each group, right? So when we calculate the deviation of each group mean, right, from the grand mean, we have to include the contributions made from every member of the group. That is why we multiply x bar for each group minus grand mean squared by ni. So if we have 3 groups, or whatever groups, and we have n1 and we have a bunch of numbers here, so we take the x bar of this and then we find x double bar, Then we subtract this from x double bar, multiply by n1, and square it, of course. And then we have x2 bar. We're going to subtract this x double bar from that, square it, and multiply by n2. Why? Because you see, when you subtract x1 bar minus x double bar and square it, that would be only the deviation for one item. Then we have to include all of them, so that means we have 3 deviations exactly like that, 1 per item. That's why we multiply by ni, n sub I. Okay, another explanation I have is this. Or you can think of what we want to calculate. We like to know the sum of square variations between groups caused by all the members of each group. For example, so basically what we want to know is, why is it that x1 bar and x2 bar and x3 bar, right here, why is it that these are different from x double bar, right? Why is this sample means different from x double bar? We want to know how much variation we have. But notice, the reason we have these variations is because of the group members. The group members actually cause that variation. So we have to calculate the variation per group member. So when I write x1 bar minus x double bar, right, squared, I have to do that for this member, for that member, and for the other member. So that means I have to do it 3 times. And then do the same thing for group 2 and group 3. So that's where the formula comes from. So for example, if this is 9 and the group has 3 members, then the variation caused by that group is 3 times 9. That is, each member is responsible for 9 square units of variation of the group from the grand mean. Alright, so that's the best explanation I can give you on that. We are not going to use the formulas directly in this course, but you want to learn the concept, so you need to know where they come from. So again, another question is, where does this formula come from? Now this one is easier to understand. So this is the variation from the group means per individual. So what we have to do here, we have to take each individual in each group, right? Doesn't matter how many groups we have to take each individual from each group and figure out how they're different from their own mean, right? So from this one, we have to have all the xi's in the group minus x2 bar and square them and add them. And then for this one, we have to do all the x's minus their own x bar squared and so forth. So to do that, now it looks like we have what? We have something that doesn't look like, x minus x bar. It looks like what? It looks like this. So where do we get this? Well, notice, if in each group, if you go and find the variance of that sample variance for that group, right? Group 1, group 2, group 3, and so forth. What's the formula to find sample variance? Well, we have to take each member of the group, right? So I have to take each member of the group. Let's say this is group number 1, has bunch of x's here, and has an x1 bar. So I'm going to take each x, right? So I have to take each of these x values, subtract x bar from it, and as a raise it to second power and add them, right? And then divide by n1, which is the sample size for group 1 minus 1. And then I have to do the same for all groups. Now notice in this structure here, if I multiply this structure by n1 minus 1, then I cancel the denominator and I get this. So my goal is to add this plus that, not the denominators, just the numerators, right? plus that, plus dot, 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 plus that. That's my goal. Now, how do I accomplish this using the S1, S2, S3 squared? Well, I'm going to multiply S1 squared by N1 minus 1. So what is that? That would be the numerator first one. This would be the second one. This would be the third one. And this would be the fourth one. Now I'm going to add, right? Add these. That's my goal. So to get the total sum of the squares of each item from their own what? Their own group means, that's what I have to do. But instead of doing this, which is much harder, I can do this, which is much easier, right? So I'm going to do this, which is much easier to do. Okay, so that's what I'm going to do. All right, so instead of adding all those, I add all this, which is much easier, and that's where the formula comes from. Okay, all right, now we can talk about the concepts. Back to concepts. So what we have is bunch of groups here, right? We have bunch of groups, and these groups have different means, right? So this is group number 1, this is group number 2, 3, and so forth, all the way to K. 1, 2, all the way to K. K groups. Now each group has a mean that is represented by this line in the middle, right? And the variation in each group is represented by this length here. That's the variation. That's another example. So you see, what we want to do is to see if the differences in the value of these means, right here, is big enough to us to reject this, that the mu's of the populations that they come from are not the same, that are the same. Yes. So the question is whether we have enough evidence to say statistically that these means are the same or not, whether we can reject it or not. And so, and this is another example. What if they look like this? Well, we don't know. Do we have enough evidence? We don't know. We have to do some calculations. And how can we know? Well, we know, we find F, and that F, if we're going to put it under what? Under a F distribution, right, is a ratio, and the ratio is MS between over MS within. These have different names: explained, unexplained, treatment, and all kinds of names. But for now, we just call them between and within. So MS between, MS within. You divide them, you get a F. You bring your F over here, and it's always a right tail test. And then that's your p-value. You compare your p-value with alpha, reject or fail to reject. That's the idea. All right, so let me show you what the distribution actually looks like when you graph it with different. So if you graph the F distribution and change the degrees of freedom of numerator and denominator, you see the shape of it changes if I change degrees of freedom of numerator and denominator. So that's our F distribution with different degrees of freedom of denominator and numerator, right? So it starts from 0, just like similar to chi-square distribution. But the formulas, of course, are much more complicated that we don't want to get into. All right, so let's go back to our discussions. So one way ANOVA table expands the t-test for comparing more than two groups or two or more groups. So scope of that derivation is beyond the level of this course, and we already talked about that. All right. So it is called F distribution, named after Sir Ronald Fisher, Dr. Fisher, who was a statistician and was a chain smoker who actually fought against science and scientific understanding of smoking and the idea that it causes cancer. For many decades, he was one of the people who was against the scientific understanding and founding that smoking causes cancer. But of course, in theory, he was pretty good and he created this distribution in statistics. But unfortunately, he was a chain smoker and trying to protect his own addiction maybe caused a lot of confusion. Okay, so F statistic is a ratio. Again, we talked about this already. And there are two sets of degrees of freedom, one in the numerator, one in the denominator. And the notation for it is F, and in parentheses, we can put 4, 10. That means degrees of freedom of the numerator is 4, and the denominator's degrees of freedom is 10. All right. So variance between samples. We talked about this again. This variance is also called variation due to treatment or explained variation. And the variance with respect within samples is also called variation due to error or unexplained variation. So MS between and MS within, and we talked about the formulas already. K here is the number of groups, and then N is the total number, the sum of the sizes of all the groups, all the samples. And this F is called F ratio or just F stat. Okay? All right. So if MS between and MS within estimate the same value, following the belief that the null hypothesis is true. So if the null hypothesis is true, then these two basically estimate the same values. So they should be the same, close to each other, not exactly the same. Or that means this number is close to 1. Now, deviations from the 1, either to the left or to the right, is a proof that we have enough evidence against the null hypothesis. Because you see, under F distribution, 1 is about right here, close to the tip right there, close to the peak, right there somewhere. So if F is smaller than 1, obviously the p-value would be a really big number. So we don't have enough evidence, right? So we can't reject. I think I said it the other way, so excuse me about that. So if F is smaller than 1, right, then we have what? The p-value is really big. We have no evidence. If it's bigger than 1, well, it depends on how much is bigger than 1. If it's only bigger than 1, let's say, let me redraw it here. Let's say this is 1 and p-value is about, maybe the F is right here, but this is still big p-value. So we're not going to reject. If it's big enough, let's say it's over here, right? Let's say it's 3 or 4 or something. Then this p-value maybe is smaller than alpha, then we reject, okay? All right, as it turns out, MS between consists of the population variance plus the variance produced from the differences between the samples. So if we have many samples and there are not much difference between them, among them, not much difference, the X bars are close, then that doesn't cause MS between to be bigger than MS within. But if there are differences, then MS between, which is in the numerator, is going to be bigger than MS within. Then we're going to capture that, we're going to calculate that F and figure out the p-value and then reject, right? All right, so MS within is an estimate of the population variance. Since variances are always positive, if the null hypothesis is false, then MS between will generally be larger than MS within. Sometimes, of course, it would be smaller, but in general, if the null hypothesis is false, right, this would be bigger than this. Now again, however, if the population effect is small, it's possible that MS within will be larger in a given sample. So it's possible to get this smaller than the denominator. So it's possible to get numbers less than 1 or numbers greater than 1. Now, if we get numbers less than 1, for sure, we're going to reject. We fail to reject. If we get numbers greater than 1, depending on how much bigger they are, we either reject or fail to reject. All right, so here's an example. We're going to do it with the calculator. So there are 3 different routes for mean driving time for the 3 routes that we talked about, right? So you can stop the video now and put these numbers in L1, L2, and L3 in your calculator, which is under Stat Edit, Enter. Put these numbers here, and then restart the video. You have to have your calculator with you. All right, so I assume that you did that now. So what you do, you go to Stat, Tests, and under Stat Test, you go to last one, ANOVA. Then it goes on home screen. Then right after it, you put wherever you have the data. Now, I have it in L3, L4, and L5. So I'm going to put L3, L4, and L5 here and put comma in between. And then press Enter. That's it. The test is done. So that's my F, and that's my p-value right there. Right? So that's my F. In this case, looks like the numerator is smaller than the denominator. And my F is that number. So if you bring this number and put it under F distribution, so that number is point something, so it's going to be right over here. So this area will be greater than, of course, it would be a big p-value. And notice the p-value here is like 77%, right? 77%. So in this case, for sure, we fail to reject the null hypothesis that these are all the same. So the null hypothesis is that mu1 equals to mu2 equals to mu3. So for sure, we fail to reject that. That means really is the same thing, right? So for example, computer program that people use on their phone, Waze, I think it's called, which is a GPS kind of program that helps you get around in the cities and be efficient in terms of time. That uses a computer program that always takes the average of time taking in different routes based on data coming from the cameras, from camera systems in big cities, to decide which route you should take that would take you shorter to get to your destination. And all of that is computerized and automatically calculated. All right, so here we have P and we have F. Now, where do we get, what if I ask you what is the numerator, what is MS between, and what is MS within? Well, in that screen, when you do this test, the screen on the calculator calculates MS between, and it kind of calls it factor. So MS between is called factor. And if you scroll down, you see another MS. This MS is MS error, or MS within, right? So MS within is called error, MS between is called factor. And these are the degrees of freedom for factor and for error. Degrees of freedom for factor, the numerator, remember the unit of the numerator is per group, variation per group. So we have 3 groups. So we have to put 3 minus 1 because we have to calculate the grand mean to get this. we lose one degrees of freedom. So we get 2. So that's the 2 right there. And for error, we have 12 total number of items, and we have 3 groups. So 12 minus 3 is 9. All right, so that means the calculator basically does everything for you, okay? And this number right here, SXP, is basically a square root of MS in the denominator. And that is an estimate for, if you assume that all 3 groups come from the same population, so that population has a sigma squared. So this number right here in the denominator is actually, go back, this number right here in the denominator is actually an estimate. If you put all of these together, it's called the pooled variance. That has a squared. So S squared is basically this number in the denominator that we found. And the square root of it is S. So it's a kind of an estimate for what? For sigma squared, if we assume they come from the same population. All right. So again, we talked about this already. So in this case, our F is 0.263, right? So we are going to what? We are going to fail to reject the null hypothesis. So the null hypothesis here is that all mu's are the same. The alternative is that at least, right, one of them is different from the others. Now, of course, this test doesn't tell us which one is different. It just says one of them is different. If you want to figure out which one is different, you have to do another test. It's called post hoc. Now, post hoc means, afterwards. So basically means after you find out that there are different, then you can pairwise, you can do them by pair. So compare these two, and compare these two with the test in chapter 10 to figure out which one is the different one, right? All right, so we can conclude using p-value, we can actually find, so if we have the p-value, let's say you have the f here, which is this number. So to actually do this by hand, you can go to F distribution CDF is under distributions in your calculator. And it looks like this. So F distribution CDF is basically finding the probability between a number and another number. So lower and upper. So we put lower, comma, upper, comma, numerators degrees of freedom, comma, denominators degrees of freedom. A calculator finds this area for you, which is the same as from the calculator. So that's the one-way ANOVA that gives you P. Based on that F, if you want to do it by hand and using those formulas, you can calculate the p-value yourself. Or we're not going to do that because calculator already gives you that p-value. So the p-value is 77%, right? So our decision is fail to reject the null hypothesis. All right, so let's do a few more. Just show you a few more of these. For a sports team, took a random sample of players regarding their GPAs for last year. So these are GPAs for the samples coming from these sport teams. So this person has a GPA of 3.6 and plays basketball. This person 2.5 plays lacrosse. So the question is, are these different? That means, are the GPAs for players in different sports actually different, or they're all the same? Well, that means they all come from the same population. That means they behave the same way, right? That's the idea. So do they behave the same way in terms of GPA, or not. So that's again one of these tests, and we can easily do it. Again, I stop the video here and go ahead and put these numbers in L1, L2, L3, L4 and run the test. Right? Again, ANOVA, stat, calculate, stat test, and then ANOVA, L1, L2, L3, L4, enter. There. That's the F, and that's the p-value. Look at that big p-value, 93%. So that means we have a strong evidence not to reject this, right? Or you can say we don't have evidence to reject it. That's the better way to put it. So at significance level of 5%, well, look at the p-value, is 92%. There is not enough evidence to reject that there is no difference in GPA among the teens. Okay, and I'm going to also talk about Excel for a second. You can do this with Excel, but in order to do it with Excel, you need to set up the Excel program to have what? The capability of analysis. To do that, you have to add these add-ins to it. So the instruction is here. If you have Excel on your computer, go ahead and stop the video and go to this Excel and then add the VBA toolkit to it. So I can close this, and let me see if I can close these so I can have more space. Here we go. Let me, so here's my Excel. Let's see if I don't lose memory space here. I show you. So you just have to go to option under Excel and then make sure the add-in is available, right? So you go to file and you go to option down here, and you see it says add-ins here. I have to go to right here, add-ins, and you see Excel add-ins, and go. You have to add these. Mine already has it, so I don't have to do it, but you put a check mark and then OK to install it. Then you have to put, I'm going to go through the instruction here. So once you do that, then you're going to go to Excel and enter data into columns in Excel. You don't even have to name them. You could name them on the top and then put the data here in Excel. Then you go to, within Excel, of course, you go to data right here, right? And then select data analysis. Once you select data analysis, then you have to pick which one do you want. We want ANOVA single factor. Notice that it also does ANOVA two factor, which we don't talk about in this course. So we pick ANOVA, you pick ANOVA single factor, and then you get this window here. Now here is where you put the data. So in Excel, you have to basically pick, right, highlight only the table, not the titles, only the table, the columns. So you highlight the column, and then it automatically goes here, coded. Excel codes the cells, like from this cell to this cell, and then press OK. And here is the answers. And notice here, first of all, is column 1, column 2, column 3. It gives you the count. In this case, they're all 5. And it gives you the sums, gives you the averages, and gives you the variances for each group. So these are S1 squared, S2 squared, S3 squared, S3 squared, S4 squared, right? These are the variances of each group, and these are the X bars, and these are the sums if you need them. Now over here, between groups, this is the SS, and this is within group SS. Now these are the denominators, right? So remember our formula was what? Our formula was F equals to MS between over MS within. And MS between was SS between divided by K minus 1. And this one was SSW divided by N minus K. So in this, you see, Excel knows that degrees of freedom here is 3, because we have 4 groups, 4 minus 1 is 3. And then how many numbers do we have? Well, we had, each group has 5, and there were 4 groups, so 4 times 5 is 20, right? We have 20 total items, and 20 minus 4 is 16, so that is this denominator. And then SSB is here, and SSW is here, so Excel divides them and finds MS's for you, and then divides them and find F for you, and then puts that F, is going to put that F in what? In F distribution, and find the p-value for you, right? And that's the p-value right here, right? And F critical is if you want to use rejection region for 5%. So it calculates it for 5%, puts it there, so that's 3 point something. Well, notice the p-value, or F, is 0.15, which ends up here. Obviously this is rejection region, that ends up way over here, so we fail to reject. We don't use this, but if you need it, that's how it is. P-value is good enough, then you use your alpha and reject or fail to reject. Okay, so that's how the output for Excel looks like. All right, so are the means for the final exams the same for all the stat class delivery types? Here's another example. There are stat delivery class delivery types. Nowadays it's only online, right? Because of coronavirus, we don't have these. But of course we had all 3. So the question is there a difference here between what final exam scores averages in these 3 samples of all the students? So here we're going to assume that they all come from the same group of population of students, right? Now the question is there a difference? That means if there is a difference, that means the online students do better or worse or whatever than do the population of hybrid students and a population of what? Face-to-face students. So if we actually have 3 distinct population that we should know about, we're going to find out in this test, right? That's the idea. Again, I stopped the you can stop the video and then put these numbers in your calculator, L1, L2, L3, right? And then we go from there. So put these numbers in L1 and L2. You ready? Okay, now you go to ANOVA, run it, look at the p-value, 54%. So we don't have evidence to reject again. Use a level of 5% alpha, right? So the answer is that we don't have evidence. All right, so are the means for the final exams the same? And so this is A, B, C, D, E, F, all the answers to these you can easily find from the calculator. So what's the null hypothesis, right? What's the alternative hypothesis? C part. What's the degrees of freedom, right, of the numerator and denominator? Again, they're given right here. Numerator is the factor, denominator is the error. Degrees of freedom are right here. And what is the F distribution? What is the F distribution we use? Is the F distribution with the numerator's degrees of freedom of 2 and the denominator's degrees of freedom of 13. And then E part is what is the F stat, and the F is what is the p-value, which we can all get from here. And the G, of course, is the decision we have to make. Okay, so here's another example again. Groups of men from 3 different areas of country are to be tested for mean weight. So the entries in the table are weights for different groups in different regions. So this is the weights of a bunch of men here, here, and here. So the question is, what is the sum of the squares factor? What is SSB? So you don't have to do this test, you just have to find SSB. Well, to find SSB, you can use calculator, right? So I stop the video and put these numbers in your calculator in L1, L2, L3. All right, now assume you did that. So now we're gonna run that test, even though we're not asked to, but that's how we can find SSB easily, right? So the SSB is given by SS factor. Where is SS factor? Right here. So that's what we have to find, right? That's SSB, and SSW is this one right here. Of course, if you don't like this, you can get the formulas and do it by hand. Well, I'm just kidding. Of course, you're not gonna want to do that. All right, so here you go. That's F, and so the question here is the same problem. What are the mean square factor, the mean square error, and the F stat? Well, we have everything here. That's the F stat right here. Mean square factor and mean square error right here. All right. All right, so I did some calculations here by Excel, actually by using those formulas. If you want, you can look at it. You don't have to, but you can stop the video and look at this and see how I got these values for SSB and SSW using these values. Take a look at it. All right, and these are the formulas I used, of course. All right, so you know that this semester we had this kind of contest. You had to guess the value of how much coin is in here, and you can win. You still have time to do that. I haven't closed it yet. Make sure you do that if you haven't. Okay, guess how much, and I put the link in the announcements, and you have it in Blackboard. This semester we did this. So I'm gonna, the problem with this is that the coins are stuck in somewhere on campus. So I have to go get them, but we can't go on campus right now. So as soon as we can go back, I'm gonna get it and find out how much is in it, because I don't know myself how much is in it. So I wanted to do a blind study, so I don't know how much is in it. So I'm going to find out and do it. Now, if you want to know what I'm going to do with this, partially is given in this video. And this video link is in the notes. You can click here or click here and watch that video. It's a professor at another college that did the same thing. Even our jar look kind of similar. But anyway, so we're gonna test, in fact, related to this chapter. So what I want to do, I want to look at your guesses, right? And I'm going to look at the guesses of female students versus male students. So I'm going to have a bunch of guesses. I have a bunch of guesses here. Now the question is, we can answer with an OVA, is that, are these the same? They come from the same population. That means, in terms of guessing how much money is in here, does it matter whether you're a female or male, right? And also I'm going to do STEM major or non-STEM major, right? And then look at their guesses and see if there is a difference. Also, we're going to take all the guesses and I'm going to add them and find X bar. And you know, something very amazing happens. That X bar is going to be very close to the real answer, which I don't even know. So that X bar is actually always happens to be what? Very close to the answer. How does it work? Well, I have guesses, really wild guesses here, but they average out to be correct actually. This is called the wisdom of the crowd in statistics, and we're testing that. It's very interesting concept. All right, so what we want to do now, I'm going to stop this. Oops. I'm going to stop this now. All right, and we are going to move on. We're going to talk about test of two variances. This is really easy. So the idea I'm going to explain right here. You can read these conditions in a second. I wait for a second, or you can stop the video and read it. But I'm going to go to the test itself. I'll let you read this, and I'm going to go explain the test first here and go back to those slides. So the idea is that we have two populations and we have two samples from them. So the question here is that the null hypothesis says something about the two variances. So it says, for example, that this is equal to the other one. So the variances are the same, or the standard deviations are the same, doesn't matter. So the claim says something about the the variances or standard deviations. So this test could be two-tailed test, or it could be what? It could be, I have them right here. It could be two-tailed test, could be left-tailed test, or right-tailed test, right? So if somebody claims that they're not equal, that's a two-tailed test. If somebody claims that sigma 1 squared is less than sigma 2 squared, that's a left-tailed test, right? And if somebody claims that sigma 1 squared is greater than sigma 2 squared, then that's the right-tailed test, right? And we always assume that they're the same in the null hypothesis. So how does this work? Again, we can use F distribution. In this case, F would be S1 squared divided by S2 squared. And F is going to be, again, having numerators degrees of freedom and denominators degrees of freedom. So the numerators degrees of freedom would be n1 minus 1, and the denominators would be n2 minus 1, right? So numerator is n1 minus 1 and denominator is n2 minus 1, right? Those are degrees of freedom. And again, the way it works is the same way. We take our f, which is very easy to calculate. We bring it over here if it's a right-tailed test and find p-value. If it's a left-tailed test, we bring it over here, find the p-value. If it's a two-tailed test, whether it falls here or it doesn't matter. If it falls to the right, we're going to find this and multiply it by 2. If it falls to the left, the same thing. We find this and multiply it by 2, right? That's the idea of this test, right? So now I'm going to go back and talk about some of these concepts. In order to perform an F test of two variances, it is important that the following are true. The populations from which the two samples are drawn are normally distributed. The two populations are independent of each other. So unlike most other tests in this book, the F test is very sensitive to non-normality. So that means if the population are not, close to normal, then it changes the p-value, right, in ways that are unpredictable. So that means it's not a good test if we are not sure if the populations the samples come from are normal or not. But we're going to talk about it in this chapter anyway. And there's some conditions here that you can read yourself. So you can stop and read. So I'm going to move on and talk about this idea. So this idea is that suppose we sample randomly from two independent normal distribution. Let sigma 1 squared and sigma 2 squared be population variances, and these two, of course, are sample variances. Let the sample sizes be n1 and n2. Since we are interested in comparing the two sample variances, we use the F ratio. So this is the F ratio. But notice that these two, if we assume the null hypothesis is true, then these two are the same and they cancel in this setup. So F is really S1 squared over S2 squared, right? So that's the idea. All right, so let's move on and do an example. Two college instructors are interested in whether or not there is any variation in the way they grade math exams. They each grade the same set of 30 exams. The first instructor's grades have a variance of 52.3, and the second has variance of 89.9. So test the claim that the first instructor's variance is smaller. So the claim is that sigma 1 squared is smaller than sigma 2 squared. So that's the alternative hypothesis because it doesn't have equal sign. And the other one would be, of course, null hypothesis. 1 equals to sigma 2. Okay? So we can easily find F and do the test. Right? So let's do that. I'm going to show you the work here. So at 10% we want to test. So here is the setup. N1 and N2 here are both the same. They're 30. The null hypothesis is that. The alternative is a left-tailed test, right? So since these two are the same, F is just S1 squared over S2 squared. Now make sure if you're given standard deviations in the problem, when you put it in the formula, this is always variance, so you have to square it. Now in this case, we are given the variance, so you don't square the numbers, right? If you're given a standard deviations, then you would have to square them. Okay, so F is that number. Now obviously, you don't even have to try to find the p-value, but let's do it. So the p-value would be the left. This is a left-tailed test, right? So this means that our F distribution looks like this, right? And this number ends up being here maybe. So we have to find the area to the left of it. And we can do that using what? Using F, C, D, F. And then from 0, because nothing before 0, right? From 0 to what? To 0.5818, comma. Degrees of the numerator, degrees of freedom is 29 and comma 29. And that's it. That's the p-value. So let's find the p-value. The p-value would be 0.075, right? That's the p-value for that distribution, right? So 0.5. You see, this is really close. So 1 is about maybe over here, right? Close to the peak. So 0.5, well, I made a mess there. Erase that. So as you see right here, 1 is about right there, right? Close to the peak. and 0.5 is here, so that turns out to be just that much. And now p-value, is it less than alpha? Yes. If alpha is 5%, then we would have to fail to reject, because that is 7.5%. This is 5%. But if alpha is 10%, we reject the null hypothesis. So we reject that. That means we support what? We support this, because we have enough evidence to reject this. That's the idea. All right. So you can read the decision here. It's very similar to chapter 9. So I'm going to move on. So here is how you do it with the calculator. Calculator has a 2-sample f-test you can use. Where is it? Is under, again, what? Is under stat tests, right? You go to stat and you go to tests and you look for what? 2-sample f-test right there. 2-sample f-test. You run that. You have to put data. If you have data, you pick data. If you have a stat, you have a stat. Here we have the stats, right? We are given the numbers. So notice right here, it says what? In the calculator, this says standard deviation of the first group and a standard deviation of the second group. So don't put these numbers, because these are variances. So when you want to put this number in here, you have to take square root of that number and put it here. The same for that number. You take square root of what? That number and put it here. Once you do that, then everything else, of course, it's easy to fill in. Oops. So we have that x, that's the standard deviation of the first group. N1 is the sample size of the first group, the standard deviation of second group, sample size second group, and you pick the left tail and calculate or draw. If you draw, you get the F distribution with the p-value. If you calculate, you just get the p-value and you get the F, right? All right, so here's another example. A grass roots group opposed to a proposed increase in the gas tax claimed that the increase would hurt working class people the most. Why they think that? Because they think that the variance of how far people live from their work is different in these two groups, professionals and working class. So that's what they believe. So they took 2 samples, one from each group, and now the question is, are these variances the same, right, or different? That means if the variances are different, the one that has a bigger variance, then the cost of going to work is widespread, right? So, you know, a lot of them pay that much. They live that far away, so they have to pay that much, right? Based on the tax on gas, right? So if they have a smaller variance, then the gas tax doesn't affect them as much, right? Because they don't really live that far away from the work. So in general, the whole population of professionals and the population of working class, they're going to be affected differently if the variances are not the same. Okay, so let us do this again. How do we do it? I stop for you to put these numbers in L1 and L2, and then we run the test, right? Here you go. You put the numbers, run the test again, 2-sample F test, and you get the p-value right there, which is really small, right? Our F is like 9.01, and this is a 2-tailed test. So what you have to do if you want to find the p-value yourself, well, we don't have to because we have it here. But f is 9 point something, so it ends up being here. So basically you have to find the area here and multiply it by 2. If you want to use a calculator, that's how I did it here. So I went to FCDF, find the area to the right of that number, and then multiplied it by 2 here. See? I got the same number. So the p-value is that. That means based on alpha of 5%, that's much less than 5%. It's less than 1%. So we reject the null hypothesis. Because the p-value is smaller than alpha, we reject the null hypothesis. That means they're not the same, right? So we support this idea that they're different. That means scientifically, we support the idea that the gas tax would affect these two populations differently, right? That's how we rely on science to actually make decisions. All right. That's the end of this video. I'm gonna come back here and where do I go? Right here, and say bye to you, and I see you, well, I don't see you in the next video, but probably in the virtual meetings that we have. Again, take care of yourself and others, and I see you around.